We agreed that you and Ted would be coming here tonight.
All right. Good morning, everybody. Welcome back. So for today, we will finish chapter number 5 uh, about gases, and then start chapter number 6, where we will cover thermochemistry. So let's pick up where we left on Tuesday. So we are talking about gases, and that was the last slide that I showed you, where we talked about the speed of different gases and how it changes as a function of temperature and molecular mass. For today, to finish chapter number 5, then we are going to talk about the real gas. Okay, so let's start with the definition of real gas. In a real gas, the intermolecular interactions and the volume of the molecules are taken into account. Okay, so let's do a quick recap here about the ideal gas first. For the ideal gas, we have no interactions and the volume of the molecules is basically zero. And every time that we have an ideal gas, we can use the ideal gas equation, which states that P times V equals to N times R times T. Okay, so that's valid for the ideal gas. However, most of the situations are going to be far from ideal, and then we have to use the real gas equation. And in the real gas equation, everything that was not considered for the ideal gas will now be considered. And the equation that describes the real gas is called van der Waals equation, and I'm showing you here on the slide. As you can see, it's sort of similar to the ideal gas equation. However, there is a correction here in the pressure, and that's the term that will account for intermolecular interactions. And also there is a correction for the volume, and that's the term that will account for the volume of the molecules. In the correction for pressure, there is a new constant that is added to the equation, and that's the A here that I'm showing you in the equation. And in the volume, there is also a new constant that is added here to correct for the volume, and that's the B constant.
Important stuff.
So A and the A and the B constants, they depend on the gas, and each gas has its own value. Here I'm showing you a table with some gases: ammonia, argon, carbon dioxide, benzene, hydrogen, and water, and the respective constants. We can see here that the constants for hydrogen are quite small, while the constants for benzene are quite large. Okay, so looking at the constants, you can try to figure out which gas is has a behavior closer to the ideal gas and which one has a behavior closer to the real gas. Higher the value of the constants, more close to the real gas is the behavior, and the other way around is true as well. So looking here at the table, hydrogen will be very close to an ideal gas, while benzene is closer to a real gas behavior. Okay, so now the question is, when are you going to use the real gas equation and when are you going to use the ideal gas equation? So the short answer for that is when I ask you to do so, okay? So we are going to face some cases that we want to compare using the ideal gas equation and the real gas equation, and then decide if the behavior is similar or different based on the conditions. And that's the idea of using the real gas equation. It's just to compare if the behavior is similar or far from the ideal gas one. And then the question here is, when does a real gas have a behavior similar to the ideal gas? So we don't need to answer the question right now. So you think about that and we will get back to that later. Okay, so with that being said, we are done here with chapter number 5. So I would strongly suggest you to go back and make sure you understand all the concepts. And the way to be good here is unfortunately practicing. Okay, so try to practice as many exercises as you can. And if you have questions, you know that you can come to office hours or you can talk with your SI instructor. Okay, if there are no questions regarding gases, we will move on to chapter number 6. Okay, so for chapter number 6, we will start talking about thermochemistry, and that's a quite short chapter as well. So here we will cover first forms of energy and energy transfer, define what is enthalpy. Then we will move on to Hess's law. talk a little bit about standard enthalpies of formation, heating curves, and calorimetry. And to finish, we will discuss the different fuels and food values. Okay, and the chapters are all named here. And if you need to go back to the book, you know where to go. Okay, so let's start defining what thermodynamics is. Thermodynamics is the science that studies the transformations of energy from one form into another. Okay, so the goal here in chapter number 6 is to calculate and predict if a reaction is going to produce energy or absorb energy. If we are going to talk about energy, let's start defining the different forms of energy. Energy can exist basically in two different forms. The first one is called potential, and the symbol is the capital U. And potential energy is associated with the ability to produce work. It's some sort of energy that you can use to produce work. Kinetics energy, symbol K, is associated with movement. Anything that moves has kinetic energy. Anything that has enough energy to produce work has potential energy. And those are the only two forms of energy that are possible. Any other sort of energy are a subdivision of potential or kinetics energy. So let's give you an example here. Let me switch screens. Okay, we defined here potential energy and kinetics energy. And here the classic example is when we move a ball from the ground all the way to the top of the hill. So we start with a ball here, and let's provide energy to this ball, and let's move the ball all the way to the top of the hill. Now that the object is at the top of the hill, we charge this object with a lot of potential energy. So we have here a lot of potential energy. The top of the hill is called a meta-stable state, which means any small perturbation, it will move back to the bottom of the hill. And if we perturb this object slightly, this object will move down the hill, and all the potential energy now it's going to be transformed in kinetics energy, because now there is movement here, and now all the potential energy was transformed in kinetics energy. So as you can see here, potential energy and kinetic energy, they can be converted between each other, but those are only the two ways that energy can exist. Potential energy is always associated with a potential to produce work, potential to do something useful. Kinetics energy is associated every time you have movement, every time you have speed different from zero. And then we can write the total energy for this system that's represented by ET. And total energy is always the sum of the potential energy with the kinetics energy. Okay. And remember, the total energy has always to be conserved. All right. Now that we defined the different forms of energy, let's talk a little bit about heat. Yes, the U represents potential energy. It's right here. Let's go back to the other screen really quick. Okay, so now let's define a very important thing in thermochemistry or thermodynamics. It's called heat. The thermodynamic definition of heat is that heat is the energy flow resulting from the temperature difference between two different corps. Okay, so if we start with a solid cube at 10 degrees and another one at 50 degrees, there is obviously a temperature difference between the two corps. When you put both in contact, energy will flow from the hottest to the coldest, and the energy flow that receives the name heat until they achieve the same temperature, and this state is called thermal equilibrium. Okay? Every time you have different temperatures, energy will flow from the hottest to the coldest, and this flow is called heat until they reach the thermal equilibrium, which means same temperature for both corps or for everybody that's involved in the system. And then here is a question for you to think about. You don't need to answer right now. Which object does have more heat? A block of ice or a flame? So think about that and we can discuss that later. When they reach the same temperature, that's called thermal equilibrium. and that means same temperature and means the energy is not flowing anymore. Okay, so think about this question, then we can discuss that later. Okay, so now let's start talking about the first law of thermodynamics. Before we go directly to the first law and define what the first law is, thermodynamics always will work with three different kinds of systems. The first system that's possible is called open system. An open system can exchange both matter and energy. For example, if you have a test tube with a chemical here and the test tube is opened, that is called open system. And the other example here is just a round bottom flask without a stopper here. The second kind of system is called closed system. A closed system can exchange only energy. Example, when you have the test tube with a stopper on the top, or a round bottom with the stopper on the top. So the stopper avoids matter to go in or to get out of the system. However, the glass can exchange energy, okay, with the outside. And that's defined as a closed system. And third kind of system is called isolated. An isolated system will not exchange matter nor energy. And the classic example of an isolated system is a thermal bottle. Okay, so you put the liquid here, the heat or the energy is going to be trapped, and the lid avoids matter to get out or to go inside the flask, and that's called isolated system. Matter cannot be exchanged, and energy also cannot be exchanged. And those are the three different systems that we are going to deal in the thermodynamics.
Professor, I have a question.
Yes.
Is to like, can you actually have like a completely real, like completely isolated system? Because like even in a thermos, it still gets cold after a while.
Yes. You cannot have a completely isolated system. You can have systems that, again, are ideal, right? And they lose like a very small amount of heat, and those we can call isolated system. But there is no perfect system. Does that answer your question?
Yes, thank you.
Uh-huh. Okay. So now that we defined the different systems, let's talk about the first law of thermodynamics. And here we are going to define three different terms here. First one is called delta U, and that's called variation of the internal energy. Q here in the equation is the amount of heat or amount of energy provided to the system, and W means work. So at this point, I would like to rearrange this equation. So let me change to the other screen here. Okay, so we have that the variation or the change in the internal energy is equals to the amount of heat plus work. So let me just do a quick rearrangement here. So let's write Q equals to delta U minus W. Okay, so let's consider here a system. So let's imagine that we have a gas, and this gas is trapped in a compartment, and one of the walls can move to the left or to the right. Q is going to be the amount of energy provided to the gas from the neighborhood. So imagine that we give energy to this gas in the form of heat. Not the best definition here. Okay, so giving energy to a gas in the form of heat, this gas can do two things with the energy that's provided. Can either store as internal energy, okay, that is one option, or produce work. And that's what the first law of the thermodynamics states. Any amount of heat provided to a gas or a chemical compound is going to be transformed in internal energy and or produce work. So imagine the amount of heat as money. If someone gives you money, you can keep the money in your bank account. So that's the same as internal energy. Or you can spend the money, and that's the same as produce work. Okay. So any amount of heat provided to the gas is going to be either stored as internal energy and or used to produce work. The substance can do just one of those or do both. It's going to depend on the system. So let's define here the terms of the equation. So let me write here again. Q is defined as the amount of heat. Delta U is the change or variation of the internal energy. And W is defined as work. The units here are units of energy. So we can use joules, which is the International System Unit, or the usual unit, cal, which means calories. Okay, for this course, I will not focus a lot in the first law of the thermodynamics. You will see that later on. However, our focus here is uh, to calculate and determine the enthalpy of chemical reactions. Okay? Remember that chemical reactions are a rearrangement of the atoms. In this process, chemical bonds are broken and new bonds are formed. In any chemical compound, potential energy is stored in the form of chemical bonds. And after the reaction, the system will release or absorb energy. The amount of energy that's released or absorbed by the system that receives the name of enthalpy. And the symbol for that is an uppercase H. And that's what we are going to focus in this course, is to look at the enthalpy. Enthalpy means the energy released or absorbed by a chemical reaction. And here we are always going to be looking for the variation of enthalpy. And variation of enthalpy is defined as delta H. Any variation is defined as the final minus the initial. And for chemical reactions, it is the same. Variation of enthalpy is calculated by the enthalpy of the products minus the enthalpy of the reagents. Again here, units. We are working with energy. The unit for energy in the international system is joule. But we can also use the usual unit cal, which means calories. If we need to convert from joules to cal or vice versa, 1 joule is 4.18 calories. Okay, so our goal from now on is to determine the enthalpy of different reactions. And the enthalpy will tell us if the system releases energy to the neighborhood or absorbs energy. With that being said, we are ready to draw energy diagrams for different types of reactions. Okay, so I will give you two examples that will cover the only two possibilities that enthalpy will change in a chemical reaction. So let's get here a test tube. And we are going to toss two reagents here in the test tube. I'm going to call reagents A and reagents B. Those reagents will react to form a compound that I'm going to baptize as AB. Okay. So let's toss them inside the test tube, and the reaction will occur. And our goal now is to determine if the reaction is releasing heat or absorbing heat. So to do that, you simply touch the outside of the test tube. And in this case, let's suppose here that when you touch the test tube, you feel the test tube hot. So that's the first possibility here. You feel the test tube hot. If the test tube is hot, does that mean the reaction is producing energy or is it absorbing energy? If the test tube got hot, that means the reaction released energy. Okay, when I mixed A with B to form AB, energy was released to the outside, and that heated up the test tube. And that's why you felt hot. Now let's draw the energy diagram for this situation. An energy diagram is going to be a graph where the y-axis is labeled energy, and we are going to represent the energy of the reagents and the energy of the products by horizontal lines. So let's start here with our reagents. So I'm going to put R here, meaning reagents, and we can write here A plus B. And then we are going to do the same thing for the product. However, we have to decide if the energy of the products are going to be above or below the energy of the reagents. Think with me. If the test tube got hot, it is because the reaction is releasing energy to the outside. If the reaction is releasing energy, what can we tell about the energy of the product compared to the energy of the reagent? Does the product has more energy than the reagent or less energy than the reagent? Well, if energy was released, that means energy was lost, which means the energy of the product has to be below the energy of the reagents. And I can write here the formula of the product. Thus, the reaction A plus B giving AB in this case will release energy. That means the energy of the products is lower than the energy of the reagents. And that was the energy released that was used to heat the test tube. When energy is released, this kind of reaction is called exothermic thermic. Exothermic means energy is released. Now let's determine the sign for the expected delta H. Okay. Remember here, delta H is the enthalpy of the products minus the enthalpy of the reagents. We can read enthalpy as the energy of the products minus the energy of the reagents. Our goal here for now is just to determine the sign. It's either positive or negative when we have exothermic reactions. Well, let's look here at the energy diagram. We know for sure that the enthalpies of the products is lower than the enthalpy for the reagents. So when you have a small value for the products and a large value for the reagents, I don't know the value of the enthalpy, but I'm sure that it has to be negative. Therefore, every time we have an exothermic reaction, energy is going to be released, which means the delta H for this reaction has to be negative. Okay, so we are going to a lower energy state. Okay, so now let's see a second example. So let's go back to our test tube. Now we are going to mix C and D, and the reaction between C and D is going to produce one single product that I'm going to baptize as CD. And after you mix CD, let's get here a green solution here. And again, we are going to touch the outside of the test tube to get a feeling if energy is being released or absorbed by the system. So we are going to touch here the outside of the test tube. And in this second situation, you feel that the test tube is cold. Exactly the opposite from the first situation. If you feel that the test tube is cold, what does that mean for the reaction? Is the reaction releasing heat, or is the reaction absorbing heat from the test tube? If you feel cold, That means the reaction had to absorb heat from the test tube to happen, and that causes the tube to get cold. So just the fact that you felt the test tube cold means the reaction absorbed energy. Okay. If the neighborhood got cold, the reaction needed to absorb energy to go all the way to the products. And here is the same thing. Let's draw the energy diagram and let's try to figure out if delta H is positive or negative. So I'm going to do the same thing that we did before. An energy diagram has the y-axis labeled as energy, and we are going to draw reagents and products using an horizontal line. And the position in the energy diagram will tell us if the energy of the products is higher, lower, or the same as the reagents. So let's start here with the reagents. I'm going to put here an R for reagents. And in this case, the reagents are C plus D. And now we think about the same way that we did before. If the reaction absorbs energy, what can I tell about the energy of the products compared with the energy of the reagents? If energy was absorbed by the reaction, that means the energy of the products has to be higher than the energy of the reagents. And I'm going to represent that by the horizontal line, P meaning products, and writing here CD because that's the only product. Therefore, in this kind of reaction, energy was absorbed by the system, and that caused the test tube to get cold, and that's why when you touch the test tube, you felt cold, because the reaction is absorbing energy to go all the way to the products. And this kind of reaction is called endothermic. Every time we have an endothermic reaction, that means energy is absorbed. And here we are going to do the same thing that we did for the exothermic sort of reaction. We have to be able to predict the sign of delta H. Delta H is the change in the energy of the system and is defined as the enthalpy of the products minus the enthalpy of the reagents. Or you can also read that as the energy of the products minus the energy of the reagents. For now, our goal is to determine the sign of the enthalpy. Is it going to be positive or negative for the case of endothermic reactions? To decide about the sign, let's take a look at our energy diagram. We know for sure that energy was absorbed, meaning the energy of the products now is higher than the energy of the reagents. If we have higher energy of the products compared with the energy of the reagents, we know for sure that the delta H is going to be positive. And that's true for any endothermic reaction. The delta H is always going to be positive because the energy was absorbed by the system. And those are the two different types of chemical reactions. Exothermic, energy is released, meaning delta H is negative, and endothermic, energy is absorbed, which yields delta H positive. Okay, looking just at the sign of the delta H, we must be able to classify a reaction as exothermic or endothermic. And we have to understand what happens with the temperature of the outside of the reaction. If the reaction is exothermic, that's going to heat up the outside. And if it's endothermic, that's going to produce the opposite effect to the outside. Okay, you have to have all those concepts clear in your head. Okay, this is a very important point that you have to understand. You have to have the concept clear. Okay, let's move on here. Okay, so now let's use the knowledge or the base that we have about exothermic and endothermic reactions, and let's apply that to real chemical reactions. So I'm showing you here two different reactions and the value for the delta H, including the sign. And what I want you to do is to draw the energy diagram for both reactions, as we did here, and classify the reactions as exothermic or endothermic. Okay? So let me give you about 5 minutes, and then I will come back, and then we will solve those problems. Okay, so let's solve, and then you will have the opportunity to check if you are on the right path or if you need to go back and revise concepts. So let's start with the reaction on the top. So we have here methane, CH4 reacting with water, and the products are going to be carbon monoxide and hydrogen. Okay? So this is one of the reactions that are used to produce hydrogen. And for this reaction, we know that the delta H is equals to 206.10, and the unit that's being used here is kilojoules. Okay. Well, so first thing, we have to be able to look at the delta H and identify if the reaction is endothermic or exothermic. In this case, if there is no sign for the delta H, that means it is positive. Okay, so you don't need to put the positive there. So you can either show or do not show. If the delta H is positive, that will mean only one thing. That means the reaction is endothermic. Just the fact the reaction is endothermic, that has to come out right out of your head. Energy is absorbed. Okay, so the reaction absorbs energy to go all the way to the products. With that being said, now let's draw the energy diagram. Again, the energy diagram is going to be represented by the y-axis label as energy. For now, doesn't matter the values. We just need to know if reagents are below or above the products. For this reaction, we are starting with the reagents right here, and you should write what the reagents are, and very important, start paying attention to the physical state of each reagent and each product, because this is going to make a huge difference. Now let's decide if the energy of the products is above or below. Well, endothermic reactions, they absorb heat or absorb energy, meaning that now the energy of the products is above the energy of the reagents. And then simply write here the products that are formed and the physical state of each of the compounds. And that's how you represent the energy diagram for the reaction between methane and water producing carbon monoxide and hydrogen gas. Now, let's take a look at the reaction below. Hydrogen and carbon monoxide produced can react, and the only product formed is CH3OH, which is methanol. And the delta H for this reaction is minus 128.33 kilojoules for the process. Okay. First thing, let's determine if this reaction is endothermic or exothermic. Now, the negative sign here, the meaning of that is the reaction is exothermic. meaning energy is released. Okay. Any exothermic reaction will release energy to the outside. Now let's draw the energy diagram for the reaction shown here. Again, energy diagram is a graph where the y-axis is labeled as energy, and we are going to represent products and reagents by horizontal lines. Let's start with the reagents right here. Doesn't matter the position. Remember to write all the reagents and the physical state. So we have here hydrogen and carbon monoxide in the gas state, and that produces only methanol. Now we have to decide if the energy of the methanol is below or above the energy of the reagents. Think with me. If energy was released, that means the system lost energy, meaning the energy of the products is below the energy of the reagents. And then just write all the products that you have formed. And that's how you are going to draw the energy diagram for this exothermic reaction. Okay, the energy of the reagents has to be, of the products has to be below the energy of the reagents, meaning that energy here was released, and the first case is exactly the opposite. Energy was inserted, was provided to the system. Okay, are there any questions to this point? Okay, if there are no questions, I think this is a good point for us to stop for today. And we will come back on Tuesday. Hope you have a good weekend. I will see you next week.
Thank you.